So what I thought I'd do is do the last example. What we want to do is try to work out the problem that's pretty close to flow over an airfoil. Okay? Steady state flow over an airfoil. And we're going to kind of get it close. Okay? So let's go back and talk about what we had constructed before from 2 lectures ago, which we normally think about thinking about a domain we're going to solve on. Okay? And in there, we're going to take a cross-section of, let's say, a wing or something like this. And what we want to solve for here is we want to solve, obviously, for the fluid velocity inside of this thing. But interestingly enough, right, we've rewritten this in terms of stream functions. Right? So in the stream function solve, what you find is this here, Laplace's equation, in this sort of complex geometry. Complex geometry because I just put a hole in the middle of it, and not just a simple hole. By the way, in the early days, fluid mechanics, when you were playing around and you didn't have a computer, you might say, hey, I got a domain here, and I got this hole in it. What should I do? Well, you know what people spend a long time doing is finding a way to transform that hole away. Okay? This is oftentimes, so for complex analysis, if we've had this, there's these what are called conformal maps and transforms, and you just say, we don't do them much anymore, but back then it was all about doing that because you don't have any other choice. What can I do to get rid of that hole? Okay, so what you do is make a conformal map, try to transform it away. Right? And you can do it for simple geometries. Okay? And the whole purpose was, can I trade that out and maybe make a more complicated, my boundary conditions are actually pretty easy on here and here, just complex geometry. Can I make harder boundary conditions but easy geometry? That's what you're trying to do in a conformal map. Trade out problems. And are you really Leah? That is the question we have today.
I am.
You are? Are you sure?
Yeah.
How would we know? We wouldn't even know. See, Leah's twin sister, apparently, right? Is that right? Yeah, twin sister. So I think maybe she came to class and Leah's at home sleeping. All right. There we go. So that's your deal. Always trying to transform out things. Always trying to get rid of your problems. And then when you do the computer, you still have problems. You just try to just address them directly. All right. Okay. So now, what were the boundaries? We wanted to impose boundaries on the fluid flow itself. Right, we wanted a velocity field coming in here with some velocity U naught. So we're trying to actually impose boundary conditions on the U field or the velocity field, but we're actually solving for the stream function itself. Right, so we're going to have to actually figure out we're going to have to impose boundary conditions on psi, not on U. Okay? So what is the relationship between stream function and velocity? Well, here you go. U is equal to phi of z, and W is equal to psi of x. Okay, this is where it kind of gets awkward, right? Because partly what you want to do is say, well, I really am interested in the U and W field, seeing the velocity field. But I'm really solving for the stream function, so I want to impose boundary conditions on U here. In fact, if we start looking at this again, you remember what we did was said, let's look over here at the left of the domain at x equals negative L along here. So this is, for that x value, what I want is U at x equals negative L to be U naught, which means I have to impose that kind of boundary condition over there. Okay? And by the way, over here, too, I don't want any velocity going in this direction. And you can also think about trying to impose something there. We're just going to kind of toy around with, like I said, I'm going to get something close to what we want to do. I'm not going to actually do the full problem. We're just going to play around with this and kind of get it managed. I'm not going to massage it too hard to make it work. Okay? I'll get something that produces nice little arrows that you can actually believe is the real problem. That's my goal today. Okay? All right. But I'm admitting it up front. I'm not lying. Unlike Leah, well, not even Leah. We don't know who this person is. Are you registered for this course? So, okay. All right, so this is what we're going to do. So everybody get that? And by the way, same condition at x equal L. And again, we're thinking about positive here. Now, when we impose boundary conditions, here's the other thing, right? Normally, you're going to pose a flux here, the derivative, but the way derivatives are imposed at boundaries is usually some dot product with a normal coming off of this thing. So these are going to have a sign change. The fluid flow is always the positive direction. The dot product's opposite signed, right? So notice which way the normal is pointing here. Notice which way the normal is pointing there. We're going to have a sign flip when we do our derivatives, boundary derivatives. Okay? Far away up there and below here, you kind of imagine that what you want is it's like as if this thing just went right through. You didn't ever see that wing. Okay? And that makes sense. When a jet flies over your head, you don't feel like this big wake of stuff hit you because you're at infinity. Okay? So that would be bad otherwise. Your houses would be crushed. We'd be running for cover every time we hear an airplane come by. But, we're down here at infinity. Happy or sad, whatever we happen to be. Okay, I'm happy because do you see how nice it is today? It's a little cold, but it's like sunshine. It's almost like we were in California. So I like the temperature. If you took don't take a temperature reading, just look outside. Okay, then you're like California. That's where we are. Who loves California? One person. Yes. Nobody else? You guys are in the right place, and if you can't raise your hand for that. All right. And by the way, if you're up here and you're like I don't know, like a duck or something, and you're flying around, if you're close to that wing and you're a duck, you're kind of toast. But if you're way up there, the plane, you don't feel it. Okay, so again, up here, fluid just kind of goes like this. So your boundaries here are no flux here and here. So to some extent, up at these boundaries, you just want to impose actually that W, which is the vertical flow. Okay, that should be 0, right? So you can imagine at Z equals plus or minus L. So up here and up here, then you can imagine, well, I have flow just parallel to this thing, and there's no flux across it. So W equals 0. Okay? Everybody go with that? All right.